Hey everyone. Thanks so much for coming. I'm Brock. I'm going to be hosting in this room today. Um, really excited to introduce Phil from Baseten, who's going to be talking about inference infrastructure.
Hey everyone, thank you so much for being here today. Really appreciate you all taking the time to join me. Is this my clicker? Do I get a clicker? Oh, I get a clicker. This is great news, folks. I got a clicker. All right, so what are we going to talk about today? Today we're going to talk about inference engineering for hypergrowth. What is inference engineering? Well, we're going to find out. So today what we're going to talk about, what is inference engineering? What are some of the hypergrowth AI products? What are the stories about both new companies, startups that are scaling from 1 to 100 million or even beyond of annual revenue faster than anyone thought possible before, and also teams within established existing companies and enterprises who are rolling out new AI products and features and gaining millions of users overnight. So we're going to talk about that dynamic combined with the rise of open source models, which are giving teams the ability to start taking control over their own infrastructure decisions. These two trends together created this field called inference engineering. We're going to talk about the principles of inference engineering and then see how these principles apply in production. So, inference is the last great market. This is like one of the claims that we've been making around at Baseten recently. And the reason that we think this is because, when you have the promise of generative AI, but then you have the, gap between the promise of the market impact and the kinds of products that can be built, but also needing to deliver this sustainably in production, that's where inference comes in to bridge the gap. So inference engineering, it's a subfield of AI engineering, which is kind of the last, or the big cycle that we're going through right now is the creation of this field of AI engineering. Inference engineering is within this field, and it's specifically around optimizing the end-to-end performance of AI-powered systems at scale in production. And a couple years ago, I've been in this field for a few years. I joined Baseten actually before ChatGPT, when we were mostly doing inference on predictive ML models. These were a lot smaller. They ran on CPUs for the most part, so it was a different world. And if you'd asked me a couple years ago, you might think that inference engineering would be limited to a handful of companies. That maybe a couple of hyperscalers, a couple of foundation model labs would need to introduce this engineering discipline within their teams in order to support those handful of proprietary models that everyone was going to end up using. But, over the last couple years, 2024, 2025, this year, AI native products have been redefining hypergrowth, and a new class of open source models has emerged that these products can actually rely on. And because of that, inference engineering has gone from something that was maybe going to be like a couple teams each at maybe 10 companies to something that every single company in the world is starting to think about how they're going to invest in. So let's talk about that first trend. Let's talk about AI native hypergrowth and how it challenges the previous definitions we had of what it means to run at scale. AI native companies are scaling fast. From a startup perspective, usually this looks like revenue. You're looking at time from $1 to $100 million ARR. I don't need to tell you how fast all of these companies out there are scaling revenue, because you're seeing it in the headlines every single morning. But with this massive increase in revenue, a lot of these companies are not really staffing up gigantic teams. These companies are growing much more efficiently from a team perspective as well, with fewer engineers supporting more users. And this trend is massive in startups, but it's also often being replicated in scale-ups and enterprise, where a company is going to start investing in an AI feature or a new AI line of business. They're going to staff it up with a small team that runs up very quickly to the scale that the enterprise is working at. So in this process, in this journey from a very small product to a very large service in a very short amount of time, what do these builders on these teams actually care about? How are they differentiating their products in this market? So number one is quality. Like, you have to have really excellent task-specific quality with evals and a clear idea of how to make make sure that your model is actually solving your use case. The second thing you need then is really excellent latency. Your product should be able to respond quickly, and it should be able to do so reliably, especially under peak traffic. Then once you have all of that, that's what powers you through that growth. But once you get big, you start to care a lot about economics, the unit economics of operating at scale, and you start to care about differentiation because 10 other companies are going to try and build the same thing, and you want to figure out long term how you're going to be different. And one tool that all of these fast-growing product teams are increasingly turning to address all 5 of these things they care about is open source models. Because now, for the first time, open source models really offer frontier performance across modalities. There are a lot of open source models. Everyone knows a couple. Everyone's heard of Llama. Most people have heard of DeepSeek. There are over 2 million open source models on Hugging Face. Actually, I had to send these slides in a few days ago, so it's probably like 2.1 million now. It's going up pretty fast. And what do these 2 million open source models give you? They give you, oh, it's got a cool animation on there. They give you state-of-the-art performance across modalities. So everyone likes to talk about generative AI in the context of large language models. We've got a lot of great large language models. We've got Kiely, we've got GLM, Qwen, DeepSeek, Llama, GPT-OSS, Gemma. There's probably been another one announced while I'm up here on stage, and I'm gonna have to put this microphone down and like go ship it really quick on Baseten, because yeah, it feels like every morning I'm waking up, checking Twitter, new state-of-the-art open source model. We got to put it up. We got to get it out there. And that's great in the LLM field. But like I said, generative AI is much bigger than LLMs. And actually in the other modalities, I'd argue that open source models tend to be even more competitive. So if you look at image models with Qwen Image, with Flux, WAN, Comfy UI, embedding models across the LLM-backed ones in particular, like for every new Qwen family, there's going to be a new Qwen embed family that's going to do amazing. Transcription, you have Whisper, you have Voxtral, you have Orpheus TTS and other speech synthesis models. Every single thing you might want to build in the generative AI world is going to have an open source model there for you. And the great thing about these models too is you can take them, you can fine tune them, you can make them better for your task specific quality. So open source models with inference engineering power everything that these AI native product builders care about. The quality, you can take the open model, you can fine tune it on your data, and then you own it. It's not like fine tuning a closed source model where you're just dropping a LoRa on top of someone else's infrastructure and hoping for the best. You own your weights, you own your model, you can use it in production forever or until you create something better. For latency, you own your weights, you put them on a GPU yourself, you can do your own model performance optimization, you can set your own latency budget, make sure that you can, trade off throughput and latency appropriately, and that you can take your engineers and you can say like, if you tell your engineers, hey, my OpenAI model is too slow, or my Claude model is too slow, there's really nothing they can do about it. You got to just like wait and hope they make it better. But if you run the model yourself, then of course you can go ahead and actually do something about it from an engineering perspective. What do you do about it? We're going to talk about that in a second. On the reliability side, you're not dependent on a third-party provider. Again, you have your own GPUs. You can keep them up. You can keep them running. On the economic side, models are getting cheaper. No denying that. If you look at the graph of token intelligence prices over the last couple of years. But even with that, AI services in general are still getting more expensive to operate. And with open models, you can come from a price taker, someone who's in the market and just takes whatever price the vendor gives, into a price maker, where you are setting your own price for inference by acquiring GPUs and running inference on that. And with all of this, you're able to build differentiation into your product. But everything that I just laid out here, it sounds really nice, but it's actually a pretty big engineering challenge. And the type of engineering necessary to realize the promise of everything that I just talked about here is called inference engineering. I'm going to introduce 3 principles of inference engineering that guide a lot of the work that we do. So the first principle is constrainability, or constraints. The more constraints you're able to introduce to your problem, the more performance you're going to be able to achieve. And I'm going to give a couple examples of that later on. The second is scale. The more scale that you're able to operate your product or service at, the more techniques become available to you to use. And the third one is adaptability. These products and services are growing and scaling fast, but there's also day-to-day fluctuations that are going to happen in your usage, in your traffic. There are going to be launches. There's going to be, random viral moments on TikTok. There's all kinds of reasons why a whole bunch of traffic might show up at your product at one time. And being able to have your inference service dynamically adjust its configuration at runtime versus have something that you've statically deployed and then have to go manually mess with is going to be massive for dealing with that. So let's talk through these principles one at a time. So the more constraints you introduce, the better performance you can achieve. What does that mean? So let's think about NFL. I love to watch the National Football League. I love watching football. And what's super cool about NFL players, they're really big, they're really fast, and they're really strong. And that's what makes them exciting to watch on the field. But an NFL player, they're big, they're not as big as a sumo wrestler. An NFL player, they're fast, they're not as fast as an Olympic sprinter. And sure, they're strong, but they're not as strong as like a power lifter. So with the specialization that each of those other three types of athletes I just mentioned are, the sumo wrestlers, the Olympic sprinters, the power lifters, in their own domain, they can outperform these fantastic athletes who get paid millions of dollars to play in the NFL. They're able to outperform them in those task-specific areas. So this is a thing that we see in open models, by the way. You see small models that are created that can do one thing like SQL generation way better than a frontier model with much more efficiency. Well, there's the same idea in inference engineering. If you have to run a specific model for just one purpose, like code completion, which we'll talk about in a little bit, you're able to constrain your universe around that problem and make trade-offs that otherwise wouldn't make sense in pursuit of optimizing for the one thing you actually do care about. The second principle is scale. The larger scale you operate at, the more techniques become available. Honestly, this one's kind of derived from the last idea, because with scale, you're able to specialize each component of your infrastructure a little bit more. If I'm only running a little bit of traffic, if I only need one GPU, that GPU kind of has to do everything. But with more scale, I can introduce parallelism. I can introduce disaggregation, for example, where for an LLM, I might run prefill on one node and decode on the other. So one's handling all my inputs and the other's handling all my outputs. I'm able to add specialization to my infrastructure and invest in more techniques at scale, because the other thing is, if I'm spending, $10 million a year on inference, like a lot of scaling companies are starting to think about, well then, if I can get 5% improvements, that's $500K right there. I just paid for an engineer to make it. So with scale comes the opportunity to invest in more techniques, do more from both a technical perspective, and invest more in the business perspective on inference. And then the last idea is dynamic configuration over static configuration. So you want things to flex at runtime. A big example of this on the infrastructure side is auto-scaling. So being able to scale GPUs up and down in response to traffic rather than having a fixed allocation that you're constantly trying to manage. But this also extends into the runtime itself. If you have, let's say, a certain batch size, maybe you have a low batch size because you want to have very good latency. As you scale up, if you're able to dynamically adjust that and start running larger batches, sure, maybe your per user latency suffers a little bit, but your system as a whole does better through this peak traffic. If you have, for example, speculative decoding, you might want to turn that on or off depending on the batch size that you're using, because at large batch sizes, you don't have enough compute left over to do the speculation in the way that you were originally planning to. There's a lot of ways that you can modify your system, that you can take a configuration that makes sense in one scenario, dynamically turn it off in another scenario, and then turn it back on once your traffic reverts to the baseline that you've kind of built for. And the advantage to doing this is it makes a much more robust and resilient system, as well as one that can get through these peaks and valleys in the traffic more efficiently. So I'm now going to transition to a few different stories where we're actually kind of seeing this in action. And the first is, building a low latency system for a really excellent user experience. So here's a problem that a customer of ours brought us. This is SourceGraph, by the way. They're a great code editing tool. And the problem that they brought us is like, hey, we need a model that responds as fast as an engineer types. I'm not the world's fastest typer. I can do maybe like 40, 50 words per minute, 60 if I'm really going on it. I'm sure there's someone in this room probably who can type at 100 words per minute, and you know who you are. So if you're typing at 100 words per minute and you're using some kind of auto completion as a coder, you need this auto completion to be able to keep up with you, or it's just going to trip you up and you're going to turn it off. When we think about human reaction time, I'm not the fastest typer. I also don't have the best reaction time. The reason I know I don't have the best reaction time is because I do martial arts. So every time my reaction time is slow, I get punched in the face. So I know that the average human reaction time is usually going to be around that 200 to 300 millisecond mark. So if you can do something in a couple hundred milliseconds, it's going to feel instant to the end user. So when you put those two things together, you've got the fast typing speed, you've got the human reaction time. You're going to want, that 200 to 300 millisecond target for your code completion. The issue is before you were seeing like the valleys down in a little under 400 milliseconds, but peaks well above 600 milliseconds in this previous system. And this is just not a reliable P99 latency that you can build this kind of product on. So SourceGraph came to us. They wanted us to help them optimize the system. We did it, and then rolled it out. And you can see, coming down to more of that 300 millisecond average latency. So what did we actually do to get that? Well, this is a great illustration of the first principle that I talked about in inference engineering, which is the idea of bringing in constraints. So if you look at the optimizations that we did for AmpTab, a couple of them are kind of generic. First off, switching to TensorRT LLM. TensorRT LLM is an inference engine by NVIDIA. It's an alternative to stuff like VLLM, SGLang, OLLAMA, all fantastic technologies in their own right, which have a good number of use cases out there that make sense for them. We've generally found that TensorRT LLM is the most performant inference engine in most cases, especially for high throughput workloads like this that are latency sensitive. So we switched them over to TensorRT LLM, but that alone is not really going to get you there. Any engine can be configured to do a good job. What really mattered is taking a close look at the constraints of their workload and then bringing in inference optimizations based on that. The first one is a big focus on KV cache reuse, specifically prefix caching. So if you think about code completion, you take a file and you want to append a few tokens to the end of the file. So the majority of this request is going to be a big input sequence. Input sequences take a long time to do prefill on, and that's going to have a high time to first token, which is going to give you a high total response time, which is exactly what we didn't want. So with prefix caching, we're able to reuse the KV cache that's calculated during prefill and basically skip that entire step for all subsequent requests that have the same information from the file. And if you think about a code file, you're probably not changing the whole thing all at once. So a big chunk of that prefix is going to be able to be reused every time. And when you think about the exact traffic pattern of something like a tab completion agent, one user is going to do multiple tab completions in the same file in pretty quick sequence. So it makes sense that we can keep this cache on the GPU itself, and then just make sure that we route the user's traffic onto that GPU that has the warm cache for their specific code that they're working on and doesn't have someone else's file cached instead. So that's an example of how you can, understand the traffic pattern of the system that you're building and use that to decide on an inference technique that makes it better. The second thing that we did, this one is actually super cool, is doing a different kind of speculative decoding called n-gram speculation. So ordinary speculative decoding works by taking a draft model or taking something like Eagle, where you train a model specifically to speculate tokens. And on every forward pass through the model, in addition to generating one token like normal, you also fill in a handful of other tokens from the draft model, check if they're correct, accept them, or reject them. And the advantage of this is you can get a lot higher tokens per second. You can complete your response much faster. The downside is if your acceptance rate is low, all these draft tokens that you're spending extra energy to create and verify are worthless. You can actually make your system slower overall if your speculative decoding doesn't work because you're just throwing away all these draft tokens you're making. Well, with code completion in particular, the syntax of code is very constrained. So you only have a few different types of tokens. You have the language tokens, you have stuff like brackets and tabs and colons and all the things that you use in the syntax of the language. And then you have some repeated variable names, you have some common patterns. Like coding the actual characters on the screen is much more predictable than, say, creative writing. And because of that, there's a specific type of speculation called n-gram speculation, where you take individual tokens and then you complete a sequence of n tokens after them into a dictionary. So rather than using a separate speculation model to generate some tokens, which is rather expensive, you do a very, very cheap dictionary lookup. And with coding, because the syntax is so predictable, you actually have a pretty high hit rate on this dictionary lookup. And you're able to generate sequences of, we've seen in production, sequences of up to 30 speculative tokens accepted on a single forward pass in a system like this. And what that gets you is, every time you do the forward pass through the model, that takes time, it takes resources. If you're able to get 30 tokens for the cost of one, in an extreme case, most times it's not nearly that high. But if you're able to get multiple tokens for the cost of one token, that's going to massively improve your system speed. Again, this is not optimization. I would not tell everyone in this room, go add n-gram speculation to your inference server today, because I don't know the use case you're building. I don't know the constraints that you have. There's probably going to be a different technique that makes sense for you and your constraints, unless you're building exactly this, in which case come find me afterwards. I'll tell you how to make it faster. But this is more of an illustration of that first point, that like the more constraints you can introduce to your system, the better performance you're going to achieve. All right, cool. Second story, flexible scale for viral launches. So I've had a couple viral launches before in my life. They're super exciting, but you're also like really nervous the whole time because you're like, what's gonna break? So we had a customer call us up and they were basically like, hey, we're gonna do a big launch. We think it's gonna go pretty well. How many GPUs do you have? And we were like, all right, well, how many GPUs do you need? Turns out that to hit the peak traffic that day, this spike up here, they needed over 1,800 H100 GPUs to process this traffic at peak. You can see in the morning, they were running at just under 400, scaled up to 1,800, scaled back down to about 600 through the course of this launch day. This is a very standard launch traffic profile. And the thing that makes this particularly difficult is that, it's very difficult to guess how many you're going to need at that peak. If you've been doing sustained at 400, it's hard to say like, okay, I'm going to need exactly 1,800 GPUs. I'm going to need them at exactly 2 p.m. And I'm going to need them for 3 hours after that, and then you can get rid of some of them. That kind of capacity planning is not really something that is possible to do. So what we have to do instead is dynamic adaptation, kind of that third principle that I was talking about, where you're adapting the system to the realities of the traffic that you're running. In this case, this is just kind of a pure auto scaling. What is cool though, and I'll show you how this works in a second, is every single one of these different colors you can see on here. This conference, we've got some like really good design. I don't know if you've noticed, like all of the design is super uniform. It's been really cool all day. So this is the one slide that I insist on having color in, because I wanted to show you that every single different one of these colors is a different cluster, many of them in different cloud providers and in different regions. So if you go to one cluster in one cloud provider in one region and you say, hey, I want 2,000 GPUs right now, it's not going to go great in most cases. So what you need to be able to do instead is draw these GPUs from these dozens of different sources. So how does that work? And how can that add reliability for some of these mission critical applications? So one thing that's important underpinning of inference engineering is the idea that, yeah, I love to talk about the runtime, the performance stuff, but the other half, the equally important half, is on the infrastructure side. Like, how do you make sure you actually get and orchestrate the hardware? And that's where something that we call multi-cloud capacity management comes in, where most people who are running big inference at a large scale are going to end up needing to build some kind of system like this, where you're going to need more resources, and you're going to need resources that are distributed worldwide. So rather than running a single cluster in a single region, you're going to need GPUs close to your users. You're going to need GPUs in regions where you can hold data sovereignty. You're going to need GPUs that are available to you from a provisioning and capacity standpoint. And to get that, and especially to get that at favorable pricing, you're going to want to make sure that you have access to GPUs from everywhere. And that's where a multi-cloud capacity management system comes in, where you're able to we're up to like 12 clouds at this point. You're able to bring these clouds on board and treat every GPU in the world basically as a fungible commodity. So that's inference engineering. A big part of AI engineering I've always thought was quality. That's really been the story of the last couple of years. Like, how do we make AI products better? And there's been a ton of work done there. AI products are actually really good now. That's why they're growing so fast. That's why there are so many models out there now that have these incredible benchmark scores and incredible live performance characteristics. Like, the quality in the AI space is really, really good. And AI engineering is continuing to evolve as a discipline. You've got new stuff. You've got like context engineering is one of the new hot buzzwords now within that space. But all of that is really focused on quality. Inference engineering, on the other hand, is the science of making AI native products faster, making them less expensive, and making them more reliable at scale, and doing all of that without sacrificing the quality that you've worked so hard to create. Thank you so much for your time. My name's, again, Philip Kiely. I work at Baseten, where we do all this. We've got a booth right across the hall over there. So come hang out with me afterwards. Let's connect on Twitter or LinkedIn. I've got pretty good SEO on my name. There used to be this doctor in New Hampshire his name's Philip Kiely. He used to be above me, but I've kicked that guy off of the first page of Google search. So if you're a sick kid in New Hampshire, you're out of luck. But if you're trying to find out about inference engineering, hit me up. So thank you so much.
Okay, thanks again to Phil. That was awesome. So we have a 15-minute break now in this room. We'll be back at 1:45, where Andre from Statsig will be talking about MCP servers. So feel free to go grab a snack or a drink and come back, or check out one of the other breakouts, whatever you'd like.